functions.
Okay.
And the first one is inverse sine of 0.1.
Have to find out what that is?
Yes.
Obviously, you can use a calculator. And I say obviously because there's no way to determine that without a calculator or a table.
Right.
Now, let's just talk about inverse sines for a moment. If I say the sine of an angle equals a ratio, that means that the inverse sine of the ratio equals the angle. And what this tells you is that you're always taking trig functions of angles to get ratios, and you're always taking inverse trig functions of ratios to get angles. Basically what you're talking about here. In other words,
Right.
on the problem you've given me, we're taking the inverse trig function of a ratio. That's the same thing as if I wanted to write it like that, equals x. X is going to be an angle. Now, whether that angle is in radians or degrees doesn't much matter. What's really important is that you realize that take trig functions of angles, you take inverse trig functions to get angles.
Okay.
What kind of calculator do you have, William?
An N-spire.
Go ahead and put that in, see what you get.
0.100167.
Is that degrees or radians?
Oh, that's radians.
You sure?
Yes.
Because with the Inspire, that's its weakest deficiency.
Right.
Is not telling you whether you're in radians or degrees and making it actually quite difficult to figure it out. So
right.
The easiest way to figure it out is to do the sine of 30 degrees. And if you get 1/2, you're in degrees. If you get something else, you're in radians.
Okay, it gave me 1/2.
That means you're in degrees, which means this answer is probably degrees.
That's strange though, because in the top right corner it indicates whether you're in degrees or radians or gradients.
Oh,
and it says radians. And then I convert
this.
that into degrees.
Take the inverse sine of 1/2. Make sure you get 30.
Yeah, I got 0.5.
Okay, so you are in degrees. And yet it's telling you you're in radians.
But when I used the function on the calculator to convert that to degrees, it gave me a different number.
Hold on a second. Let me get my Inspire out, because I have one. Trying to figure out what's going on here. Well, my battery is critically low. That's not good. Let's see if I hit. I'm going to take the sine of 30, and it gives me 1/2, but I don't see anywhere on my screen where it tells me I'm in radians or degrees. You say in the upper right?
Yeah, it should be just to the left of the battery.
Yeah, I don't get that. Maybe I don't have it on display. Maybe that's the problem. I've never had it on display. And
Uh,
the thing I remember is that when I went to set it, it was very difficult. I had to go to, it was hard to set the radians or degrees. Here, let me plug my thing in here.
yeah, I don't remember how to completely change it. I know how to convert one answer to one or the other, or gradients, or whichever.
Here, let me do this one you just gave me here. Let me make sure I get the same thing. The inverse sine of 0.1. Now, see, I get 5.7 degrees,
Yeah,
which is probably 0.1 radians. Not sure what's going on. But your calculator is telling you you're in radians.
yes.
Okay, well, that answer you got then is radians, because when I do it, I get degrees, and I know I'm in degrees because when I took the sine of 30, I got 1/2. Whereas if I was in radians, taking the sine of 30 would not give me 1/2.
Right.
Okay. All right, so you're in radians. Now, you can always convert that to degrees if you want. Let's see, you would multiply it by 180 over pi, and that should give you, if you take that answer you got and multiply it by 180 over pi, you should get 5 point something. See if you do.
Hmm.
Yeah, you're gonna get that, I think. Let's see. Yeah.
Yeah, 5.742, so approximately.
Okay. So the most important thing is that you know what you're in. You must, or somebody must have set your calculator so that it shows that. And mine apparently hasn't been set on that, because mine does not show that. Maybe you have a more updated version of it. All right, what else you got?
Inverse tangent of 0.
Okay.
One question.
Uh-huh.
For this section, the directions say find the exact value.
Uh-huh.
So does that mean without a calculator or with a calculator?
Well, the last question you had, there's no way to really give the exact value of that. You have to round
Right.
it off. This one, you can give the exact value.
Right.
In other words, this question is going to relate back to either one of those triangles, the two special triangles, or it's going to be a whole number. Well, what angle is the tangent equal to 0? Let me draw the tangent curve. Here's one period of the tangent curve. It's minus pi over 2 to pi over 2. That's 0 right there. So, and the horizontal axis is your angle.
Hmm.
So the tangent of 0, in other words, if I look at this curve on the right only, I can say that the tangent of 0 degrees or 0 radians, doesn't matter, is equal to 0. Therefore, the inverse tangent of 0 equals 0. And that's what your calculator should give you. What does it give you?
0.
And this probably you're not supposed to use the calculator on this. Yeah, okay. I guess there's a couple of ways to do this. The best way to do these problems without a calculator is to know the graphs.
Right.
But there's another way. You know that tangent of, no, not sure about inverse tangents. You know tangent of theta equals sine of theta over cosine of theta, right?
Yes.
Okay, well, the only way that the tangent of theta can be equal to 0 is if the sine of theta is equal to 0. In other words, whenever you have 0 equals a quotient, the numerator of that quotient must be 0, has to be. So saying that the tangent of an angle is equal to 0 is basically also saying that's where the sine of the angle is equal to 0. And if you know your sine curve, sine is equal to 0, the sine of 0 is equal to 0. So therefore the tangent of 0 is equal to 0. And as long as you know that, then you'll be able to answer that without a calculator.
Okay.
What else you got?
So this one is the same directions. Find the exact value.
Okay.
The inverse sine of negative root 3 over 2.
All right, now this one we can use our triangles. What are the dimensions on the triangle on the left?
Across from the 30 is 2.
Always 1.
Always 1.
Well,
Right.
the reason I call these, I actually personally name these my unit special triangles. And I use the word unit such that the side opposite the smallest angle is always 1. So that's 1, that's 1, that's 1. On the triangle on the left, the side opposite the 60 is root 3. And the hypotenuse you can always figure out, but it's 2. And over here you can always figure out the hypotenuse, which is square root of 2. So it's those dimensions that are what's important. In other words, those dimensions are what allow you to calculate all the trig functions in the first quadrant. Ones that are 30, 45, or 60. Well, which angle is the sine equal to square root of 3 over 2?
Uh, 30 degrees.
No. The
Sorry, 60 degrees.
sine of 30 would be 1/2.
Right.
The sine of 60 is root 3 over 2. Okay? So we're looking at a 60-degree angle. I'm going to put it in parentheses because that isn't necessarily the answer. This tells you the angle. Now, when they give you inverse sine, if they give you a positive number, it's first quadrant. If they give you a negative number, it is fourth quadrant, and it's a negative angle that's the same as the first quadrant. In other words, instead of 60 degrees, it's minus 60 degrees. And that's how you do the sine and the tangent.
Okay.
Okay? Now, turns out that minus 60 is the same as plus 300. But your calculator's never going to give you the plus angle. The calculator is going to treat the inverse sine in one of two ways. If the argument is positive, it's going to give you a first quadrant. If the argument is negative, it's going to give you a negative angle in the fourth quadrant. That's it. It's never going to give you the third quadrant. In other words, there's a third quadrant of 240 degrees, where if you took the sine of 240 degrees, it would give you this answer, negative square root of 3 over 2. But because they want to treat inverse trig functions as functions, for it to be a function, it can only give you one answer. It can't give you two answers. You don't want the calculator telling you that that's minus 60 degrees and, oh, by the way, it's also 240 degrees.
Right.
It's going to give you either the first or the fourth quadrant, and that's it. Will not give you a second quadrant answer for a positive angle. In other words, if I said inverse sine of 1/2, it's going to give you 30 degrees. It's not going to also give you 150 degrees, despite the fact that the sine of 150 degrees is also positive 1/2. In other words, it does not give you all the answers in the unit circle. And it's important to understand that. It only gives you two of them. Whereas when you go to solve equations, if I said to you the sine of x degrees equals negative root 3 over 2, and x is anywhere in the unit circle, you're going to come up with minus 60 degrees is one answer, and another answer is 240 degrees. Both of those, when you take the sine of that, you will get that answer. So it's very important to distinguish here between the principal values and the value, all of the values that satisfy this in the unit circle.
Okay.
I can probably explain a little easier with just doing more problems.
Okay.
What's the next?
The inverse tangent of negative 1/2.
Which quadrant is that going to be in?
Quadrant 2.
No. In other words, tangent is the same as sine. Your inverse tangent's answer is going to be either quadrant 1, if it's positive argument, or quadrant 4, if it's a negative argument.
Right.
Now, we don't have any way of doing 1/2. That's not one of our common angles. In other words, notice that nowhere on here is the tangent of any of these three angles 1/2. So that's an odd one. You have to use your calculator for that. And the answer you're going to get is going to be a negative angle, going to be in the fourth quadrant. What is it? You're in radians.
Do in radians or degrees?
Well, last time you were in radians. What does your teacher want? Does he want the answers in radians or degrees, or does he care?
I don't think she cares all that much, and there's no directions on the
Okay.
on the home.
So it probably doesn't matter as long as you know what it is.
Right.
And like I said, there's a couple, we've already done one problem on your calculator and it was clear you were in radians. So what's this give you?
Negative 0.46.
And that's radians. And that's fourth quadrant. Each
Right.
quadrant is pi over 2, and pi over 2 is about 1.57. So this number is about a third of that. So you're looking at something very close to a 30-degree angle, but
Right.
not exactly. Do you have a quick and easy way of converting from radians to degrees, or do you have to go through the...
No, it's
Pretty easy?
yeah.
Okay, it's like a one keystroke.
Yeah. And then you click a key, and then it gives you options to convert to decimal degrees, gradients, or radians, and then it'll convert it for you.
Okay.
So it's negative 26.5 degrees.
All right.
So yeah, right around negative 30.
Notice that is a fourth quadrant angle, negative 26.5 degrees. Okay. And that is also 0.46 radians. But notice that when you're dealing with a negative angle that's less than pi over 2, you're going to always be in that fourth quadrant. So if you were to put into your calculator, what's the inverse tangent of positive 1/2, you're just going to get that angle, the same thing, 0.46 radians or 26.5 degrees. So with tangent, you either get first quadrant or fourth quadrant, just like sine. Cosine is different. If you put a positive argument in for cosine, you're going to get first quadrant. If you put a negative argument into inverse cosine, you're going to get second quadrant. In other words, the two primary quadrants for inverse cosine are first and second, not first and fourth.
Okay.
Okay? I'm sure you'll have one coming up.
Okay. So this next problem is a word problem.
Okay.
And I'm sending you two pictures.
Okay.
One of which is the table of data, and then the second one is all the different parts to the question.
Okay.
Oh, I sent it to the wrong place. I'm sorry. I sent it to your phone number.
Yeah, actually that doesn't work with my phone. So if you can send it to my email, and send it to my David Cowan 1949 email.
Okay.
Actually, if you send it to the other email, it needs to get forwarded and it takes extra time. While you're doing that, you're very familiar with this triangle, I'm sure.
Yes.
You know this angle. Theta. Probably not. Because they may talk about this triangle 100 times by the time you've reached your math level, but they never talk about theta. Well, how would you solve for theta?
The inverse function.
Give me an exact answer. Inverse what? Of what?
Inverse sine of 3/5.
Yeah. And that will give you that angle, which is about 37 degrees. So this is an excellent place where you realize the value of inverse trig function. In other words, lots of times we're solving for angles. We're not always solving for ratios. We're solving for angles in a ton of problems. And whenever you're solving for angles, you're going to end up using the inverse trig function.
Right.
Check my email here and see if it's come in. It has. Which one should I open first?
The one on the right.
Left?
On the right.
Ah, okay. A word problem dealing with sinusoid functions.
Yes. So I put all the data in a table on my calculator, and then put all the points on a graph. But when you open up the next picture, the first one of the directions is find a sinusoidal function of the form that best fits the data by hand. So
Okay.
rather than using the calculator function.
Does the problem start here where it says monthly temperature, or does it start above? Is that a different problem?
It just starts by at monthly temperature.
Okay. All right. So in order to come up with the sinusoidal function, we need A, B, C, and D, correct?
Correct.
All right. A is always the maximum minus the minimum divided by 2.
Okay.
So the maximum is 56 minus the minimum, which looks to be 24. I guess minus 24.2. So divide that by 2. What do you get? You get 31.8 divided by 2 is 15. No. Yeah.
15. Yeah.
15.9, right?
Yes.
That's A. B. B has to do with the period. We know that for a sine function or cosine, B is 2 pi over the period. What's the period here?
Is it 12?
Yeah, it is.
12 months.
So that would be 2 pi over 12. So B is pi over 6. Phase shift. Well, first of all, let's figure out D, because it's the next easy. How do you get D? Take your maximum, add it to your minimum, and divide by 2. That's D.
Oh.
Okay? So A and D are very easy. A is your max minus your min divided by 2. D is your max plus your min divided by 2. So D gives us, I believe, 40.1. Correct?
Yes.
All right. So if there were no phase shift, then our function would be y equals 15.9 sine of pi over 6 times x minus some phase shift plus 40.1. And if the phase shift were 0, then it would just be what I've written there. The problem is that the sine curve looks like this. In other words, our table starts at the low and then goes up to the high and then comes back down to the low.
Right.
So that's not a sine curve. Our sine curve starts at a middle, goes up to the high, comes back down to the low, and then comes back to the middle. So what would be a better curve to use than the sine curve?
Cosine.
Okay, let's look at the cosine curve. Cosine curve starts at its high, goes down to its low, comes back to its high. Well, that's the opposite of this, right?
Right.
So what should I use? Negative cosine.
Right. Okay.
If I use negative cosine, which is a reflection of the cosine curve, perfect. Starts at its low, goes up halfway through its period to the high, turns around and comes back down towards the low, which is exactly what this is doing. And there would be no phase shift, but only if I use the negative cosine curve. So I'm going to replace sine with cosine, and I'm going to put a negative sign in front of the amplitude. And I'm going to erase the C because there does not appear to be any phase shift. Now, let's talk about if I gave you that sinusoid function, how would you graph it? Well, you wouldn't quite graph it the way my graph is because my graph doesn't allow for a D. So the way I would graph it, whenever you have a vertical shift, best thing to do is to always do that vertical shift first of all.
Right.
In other words, I'm going to go up 40.1. I'm going to draw a dotted line to represent my new horizontal axis of symmetry. And I'm going to draw a negative cosine curve. Well, the negative cosine curve is going to start at 24 degrees. I'll round stuff off here. And it's going to go to a high of 56 degrees. You with me?
Yeah.
And it's going to take exactly 12 months to complete one period. And it's going to look like this. Now, if you were to go to this curve, it would fit this table perfectly. It would also fit this function perfectly. In other words, if you were to put 6 in for x, the cosine of pi is minus 1, it's minus 1, which makes it 15.9 plus 40 gives you that 56 degree. In other words, that's 6, which is the month of July, and it gives you your high temperature. In other words, once you have the sinusoid function, you don't need the table anymore. You could take this sinusoid function and plug in any number between 1 and 12 for x. You would get a very, very good approximation of what the average monthly temperature was for that month. while I thought we had good audio quality, but it's starting to mess up. Here, let me call you.
Yeah.
I'll call you.
Okay.
Ah.
Is that better?
It's a lot better. I mean, the audio sucks, but not having that static is,
Yeah.
it's amazing how you don't really notice it, and then you start talking over it, and then when you switch to a audio without the static, it's an unbelievable difference. I don't know if that's your experience on your end or not, but it makes a huge difference on my end.
Yeah, it does for me too.
All right. So anyway, that's the way you're going to handle any problem that is a word problem regarding periodic behavior. And temperatures do that. In other words, temperatures tend to have a period of exactly 12 months, and they'll go from the cold reading in January to a hot reading in July and back again. So most temperatures, regardless of whether you're in Juneau, Alaska or not, are going to be negative cosine curves. They're going to start at their low, and they're going to go up. Let's talk about that with another type problem, just because I can explain it, I think, a little better. Let's say you have a Ferris wheel that goes counterclockwise, like that. Okay?
Okay.
And you're trying to model the height of a person based on time. And the stands are right here. This is where the person gets on. What function are you going to want to use? The sine, cosine, is it going to be positive or negative? Here's what the sine does. Here's what the cosine does. This person is getting on at the mid-height, right?
Right.
Then he's going up.
Sine.
Yeah, and then he's coming back down to the mid-height, and then he's going down to the low point. So it's perfect for a positive sine function. Now, let's say the person, instead of getting on where I've drawn it, let me redraw it. Let's say the entry point is right there. Now, he's getting on at the lowest point of the Ferris wheel, and he's going immediately to the highest point. Well, that's a negative cosine curve.
Okay.
Because I'm getting on at the lowest point, and I'm immediately going to the highest point. And I'm going back to the lowest point. So, if you had a Ferris wheel where you got on right there, now you're talking about a phase shift. In other words, you're not getting on at the lowest point or the highest point or the middle point. You're getting on at a point that might look like the following. I'm not getting on at the midpoint. I'm getting on at a lower point, but maybe something like this. In other words, I'm getting on right there. I'm still going up. Actually, I didn't draw that right. I need to phase shift it differently. I need to phase shift it like this. In other words, the curve I've drawn at the bottom might represent this model. In other words, I'm getting on not at the lowest point and not at the middle point, about halfway between the lowest point and the middle point. And then I'm going to go nothing but up until I reach there, right there. And then I'm going to, in other words, when I reach the top of the Ferris wheel, I'm at this point here, and then I go from the very top all the way back to the bottom in this movement right there. And if they gave you a Ferris wheel problem, here's the maximum, there's the minimum. You can get A and D out of that. You determine whether you want to use sine or cosine or negative sine or negative cosine based on what the Ferris wheel is doing. And you determine phase shift based on this angle. If that's a 45-degree angle, then this drawing I've drawn right there is fairly accurate. You're exactly halfway in between the minimum and the midpoint.
Okay.
All right, let me take a look at your other picture here. There any more questions on this particular problem?
No, that was it.
Okay.
Oh, sorry, I need to send you 2 more pictures.
Okay.
It's the same format same format, just different data.
Okay. So which one are we doing on this problem here? Or this page?
Okay, sorry, can you repeat that?
Yeah, this second page you sent me?
Yes.
Which problem are we looking at?
Oh, it's going to be number 20 below it. I just sent you another picture of the whole thing.
Oh, I see. This 20 is a different city.
Yes.
Oh, okay. Hold on a minute.
And it's the same problem.
But it's the one on the left that you want me to look at?
Yes.
Okay.
So I think I have A, B, and D. I'm confused on how to get C.
Well, with these temperature problems, usually C is 0. And the reason is that you're not hopping. In other words, January is always the coldest month, right?
Right.
So you're always hopping on the sine function or the cosine function at a minimum or a maximum, hardly ever a maximum unless you're in Australia. Then January is the warmest month. But as long as you're looking at a table like this where January is the lowest and July is the highest, then you're generally looking at no phase shift. You're not going to see phase shifts on monthly temperature charts because January is the lowest. In other words, this again is going to be a negative cosine curve with no phase shift. In other words, this one's not really going to be any different than the Alaska one except for the numbers. And again, take your high minus your low, divide by 2, that gives you A. Take your high plus your low, divide by 2, that gives you D. And B is always, the period's always 12. So B is always pi over 6, yeah. Now, this sinusoid curve can be applied to 1,000 different periodic type behaviors.
Right.
Temperature is just one of them. And the reason they start you off with temperature is because there's no phase shift. So it tends to be a little easier, as opposed to the Ferris wheel problem, where you can easily draw the entry point at some place that's not the bottom or the middle, which means you're going to have a phase shift on the Ferris wheel problem. And you just have to figure out what it is. And those are going to be a little harder. But these temperature problems, you're not going to be dealing with a phase shift.
Okay.
Not as long as January is the coldest month. Now, let's say they did give you, I wish they would have actually, give you average monthly temperatures in Australia. In other words, the southern hemisphere, where January is the hottest month, July is the coldest month. Then, instead of using the negative cosine curve, you would be using the positive cosine curve. In other words, you would be entering at the peak, going down to the low 6 months later, and coming back to the peak 6 months after that. Still have a period of 12, but you would be using positive cosine instead of negative cosine.
Okay.
Now, I see they want you to use a graphing utility to draw a scatter diagram. So that's why you said you had all these in your calculator for the previous problem?
Yes.
Now, so what are the instructions on this? The top of, I see. A is the first instruction. Use a graphing utility to draw a scatter diagram. Okay. What you'll see on that scatter diagram is something that looks very similar to a negative cosine curve. In other words, if you were to draw a negative cosine curve through the dots, that should approximate the sinusoid function pretty well. You know what I mean? In other words, what I'm talking about is doing this. Here, hold on a second. In other words, you're going to have a January point there, and you're going to have a December point when you get back down to it there. Your July point is going to be there, and you're going to have points there, and there, and there, and there, and there, and there, and there, such that if, in other words, if you draw a scatter diagram, that's what it should look like. And then if you connect the dots, knowing that it should be a cosine curve, looks like that. That's a negative. It's a negative cosine curve. Let me look at the rest of these instructions here. Looks like I need to go to the other one. Yeah, hold on a minute.
That's weird. When you use the calculator to find the equation that best fits the data, it gives me a sine function.
Okay. What kind of regression? What kind of regression did you choose? Because there's a lot you can choose. You can choose linear. You can choose quadratic. You can use exponential. Did you choose sine?
Sinusoidal regression.
Perfect. That's what you want to use. In other words, because you know this fits a sinusoidal pattern. So you want to use sinusoidal regression. And it should go very nicely through the scatter diagram. In other words, it should be almost a perfect sinusoidal function. Now, when I say that it's a negative cosine curve, it's still a sinusoidal function. Just because it's called sinusoidal doesn't mean it has to be sine. It can be sine or cosine. Okay, and now they say part B, by hand, figure that out? Well, we've already figured out that delta is 0.
Yeah.
And you know what A is? Oh, I don't like that. They use B to be your vertical shift?
Yeah, the way that's not how our teachers taught us, but in the book it's
Okay,
very
well, as long as you know. In other words,
Yeah.
typically omega would be B,
right.
delta
It
would be C, and B would be D. So the letters they use doesn't really matter. However, what does matter sometimes is whether that's inside the parentheses or out.
It should be out.
Well, as long as the phase shift is 0, then it doesn't matter.
Right.
In other words, there's really no should. And in fact, I've always preferred the omega to be outside the parentheses, but
Yeah.
when you study calculus, you will see, this is why sometimes it's inside the parentheses. Because sometimes when it's inside the parentheses, it's easier to work with from a calculus point of view. Not so much from any other point of view, but from a calculus. I could never understood why anybody ever gave you the function with it inside the parentheses until I got to calculus. And then I realized there's times where you can use sum and difference when it's inside the parentheses. You know, this, you probably haven't gotten to that yet, have you? The sum and difference formulas?
No.
Okay, yeah, that's coming. But that's why it's a format. Is sometimes it actually works better if it's inside the parentheses.
Okay.
All right. Now, so by hand, you know how to come up with that, right?
Yes.
Okay. And then part C, you know how to draw it.
Yes.
Your calculator, I guess, did that. And, okay, part D is use the graphing calculator to find the regression, the sinusoidal regression of best fit. And you'll find a very nice fit. And finally, draw the sinusoidal function of best fit on the scatter diagram. And
I'm not sure what to do with that because it's almost the same thing.
Yeah, it is.
I'm
I'm not quite sure what the difference is between C, D, and E. In other words, I guess C, you would draw it based on your function.
Right.
D, you would draw it based on the table of information you've put in using the sinusoidal function of best fit, which you've done already. And E, I'm not sure what the difference between C and E is. Don't they say the same thing? Not quite, but close. Yeah.
Yeah, pretty much.
Well, okay, not really. In other words, C, you're drawing the function you came up with.
Right.
Whereas
E is
E,
the one that the calculator.
yeah, E is going to be the one the calculator came up with. Well,
even so, they're so similar.
They are.
There's no point.
Yeah, I agree totally with you. I don't think there's any point either. And we don't need to really spend any more time on that.
Yeah, drawing it by hand would just look like you drew it poorly.
Well, this is drawing it by hand. With this being, what was it, 80 degrees? This being 34 or something like that. That was the low. And the high was 80. And which means the whole thing, this is not the real x-axis. This is my line of symmetry right there. Whereas the x-axis is somewhere down there. You with me?
Yeah.
In other words, That's why you always want to start with D, or in your case, B, as in boy. In other words, place the horizontal line of symmetry on your graph, first of all. And then draw whatever curve you're going to draw above and below that horizontal line of symmetry. And that's how you get D, is you add 80 to 34 and divide by 2, and that gives you that number right there. Okay? And that's your vertical shift also. Now, phase shifts are definitely a little harder to deal with, because you have to figure out, you'll notice that on the, when I talked about the Ferris wheel problem, getting on from the side, that involved a phase shift, and it was totally dependent on the angle. That's going to determine your phase shift. In other words, if I get on right there at a 45-degree angle perfectly, well, my phase shift is 45 degrees, or pi over 4 radians. In other words, if the entry stand to get on is right there, and the Ferris wheel is going there, then I've got to get on somewhere before the midpoint, before right there. So I would have to phase shift this thing. Notice that I would want to get on right about there, halfway between the low point and the midpoint. So I would phase shift it so that it looked like that. And notice that my entry point right there is halfway. Well, it's phase shifted by pi over 4 to the left.
Right.
And sometimes maybe they'll build the platform up there. So you don't get, in other words, you climb up a bunch of stairs and you get your entry points right there. Well, then that's a phase shift in the other direction. You're actually getting on between the midpoint and the peak, heading up. So you'd be getting on right there. And that's where you would want it to start. So you'd have to phase shift the original black curve to the left. More than originally. Now, phase shifts can mean that instead of using a negative cosine curve, maybe you use a positive sine curve phase shifted in the other direction. Both are equally sound. The general rule of thumb is you use cosine or sine depending on what gives you the least phase shift. If you can use cosine with a pi over 6 phase shift, as opposed to sine with a 5 pi over 6 phase shift, then you use the cosine.
Right.
Either one of them, you're going to have to use a phase shift. But use cosine or sine depending on what gives you the least phase shift. Unless the problem specifically says use a cosine. Then you deal with the cosine and figure out whatever the phase shift has to be based on that. But this is a very important concept of starting from the middle and going up, or starting from the top going down, or starting from the bottom going to the top. And the Ferris wheel actually illustrates that the best. It's kind of like the unit circle almost. And in fact, that's how they get the sine curve from a unit circle, is very much, it's like cutting the string and pulling it, and you end up with a sine curve.
Okay.
All right, William, I will let you go.
All right.
Hopefully I've helped a little bit on that. We didn't get to really deal with any that had phase shift, but it doesn't look like they've gotten. And they may not actually give you one like that. They may, though.
Right.
And you just have to figure out. And the secret to whether you're right or wrong is to plug it in. In other words, if you come up with a formula and you're not sure it's right, remember that you're always solving for the height of the person in this Ferris wheel problem. So you can always test your formula. You know that if the person is getting on at the bottom, their height is 34 feet above the ground. At the top, their height is, say, 94 feet above the ground. So if they're getting on at the bottom, you know you're getting on at a minimum point and going directly to the maximum. That's negative cosine curve. And Ferris wheel or any other kind of problem like breathing or music or anything, always keep that in mind. Where you're at on the sinusoid or the cosine curve. In other words, are you starting at a midpoint going down? Say you were starting at a midpoint going down. Say this Ferris wheel was going the other direction and you're getting on in the dead middle. Well, if you're getting on in the middle and going down, that's a negative sine curve. That's what negative sine curves do, is they start in the middle, go down to the bottom, then go up to the top, and come back down to the middle. All right. William, I will talk to you next time.
All right. Thank you very much, Mr. Count. Have a good night.
You're welcome. You too. Bye-bye.